In this video, I want to look at the molecular orbital diagram for secondary diatomics for which sp mixing cannot be ignored. So anything nitrogen and left, nitrogen, carbon, boron, beryllium, and lithium. I want to take as a starting point what it looks like without sp mixing, O2, F2, and diatomic neon. Now, diatomic neon obviously doesn't exist as a neutral species because the bond order would be 0, but diatomic neon cation could exist. Okay? And without sp mixing, we know that the molecular orbital diagram has a sigma 2s, a sigma 2s star, a sigma 2p, pi y and pi z, pi star y, and pi star z orbitals, and then sigma 2s star. And we know that it takes the overall shape of a mace or a scepter, regardless of how many electrons are actually in there to fill it. Furthermore, we know that sigma 2s and sigma 2s star are symmetrically distributed around the original 2s energy level. And we know that sigma 2p and sigma 2p star are also symmetrically distributed about the 2p energy level, as are pi y and pi star y and pi z and pi star z. So this is without sp mixing. When we have a big delta E between the 2s and the 2p orbital energy levels. And we know what those orbitals look like. We know that sigma 2s is a single sign on the wave function, just one big lobe with no nodes. Sigma 2s star has removed some of its electron density and has a single node between the nuclei in the xz plane. We know that sigma 2p has a large lobe in the center, two nodes, and it's lower in energy than pi y and pi z. Because the electron density can center itself between the nuclei where it does the most effective job of attracting both nuclei and binding. And then pi star y and pi star z have a kind of cloverleaf effect with a new node in the middle, as well as the original node. Pi star z looking the same, except 90 degrees apart. And then finally, sigma 2p star which has three nodes, two original nodes that were there for the ordinary 2p x orbitals, and then the new node where the 2p x orbitals are destructively interfered in the middle. So we know what these look like. The pi system isn't going to change with sp mixing because the s orbital can only interact with the other p orbital that has the same symmetry, that has sigma symmetry. So pi y and pi star z, and pi star y and pi z and pi star z with sp mixing are going to look the same. Those orbitals are going to come over in exactly the same location, and they're going to be symmetrically distributed around the original 2p orbital energy level, just as they were before. But there's going to be a change in the sigma system now, because we're going to get mixing if the 2s orbital energy level is much closer to the 2p orbital energy level, so we have a small delta p. Now we have to consider that the 2s and 2p orbitals are going to interact with one another. I don't want to try to add, right? I don't want to try to do do 4 orbitals at a time. The low energy orbital with the sp mixing will actually be created from psi 2sa plus psi 2sb plus psi 2pxa plus psi 2p coefficients in front of them. Let's call them x, y, and z, and w. I don't want to do that. That's going to be annoying. But what I can do is I can use a new symmetry operation so that I can combine just 2 orbitals at a time. I can notice that the symmetry is different for sigma 2s and sigma 2s star. So I can define a new symmetry property. Sigma 2s is what we call a Gerada orbital. And sigma 2s star is what we call ungerada. And furthermore, sigma 2p also has Gerada symmetry. And sigma 2p star also has ungerada symmetry. Gerada refers to no change in sign on the wave function. Reflected through a plane perpendicular to the bond axis, which in this case is the YZ plane, and bisecting the molecule. And ungerada refers to the opposite. Where the sign on the wave function changes when reflected through that plane. So the YZ plane, which is the one that bisects the molecule, when you reflect the sigma 2s orbital, the sign on the wave function is positive, so there's no change in sign. But when you reflect the 2s star orbital, the positive lobe and the negative lobe, when they reflect into each other, there's a change in sign of the wave function. Here, again, it's symmetrical, minus lobes on the outside, positive lobe in the middle, so when I reflect it through the YZ plane, there's no change in sign. And here, plus, minus, right, there's a change in sign. Because conservation of orbital symmetry must be met, only orbitals of the same symmetry can interact with one another. I can create 2 new orbitals by adding sigma 2s to sigma 2p and then subtracting them. And I can create 2 new molecular orbitals by adding and subtracting sigma 2s star and sigma 2p star. So I ignore sp mixing as an intermediate step that's going to get me to the final answer. I create sigma 2s and sigma 2p, and sigma 2s star and sigma 2p star, but then I'm going to interact them with each other in order to get the final molecular orbital picture. So what's that going to look like? Well, if we take it out of the blob and look at it like the orbital would look if you just plotted the radial probability function, I squared, right? The orbital would look like this. And then when we sweep it in 3 dimensions, we get a blob that's a symmetrical kind of cucumber shape. And sigma 2p would look like this. these two orbitals. I know that the lower energy orbital will take a larger contribution from the lower energy orbital, so that I know my new sigma 1, which I'm going to call sigma 1g. Right? It'll still have Dorada symmetry, it has to, can't change symmetry when we interact orbitals. Sigma 1g is going to be formed by multiplying some coefficient times the sigma 2s orbital, and then adding to it a smaller coefficient times the sigma 2p orbital. So it'll be closer in energy to the original sigma 2s orbital, thus it takes a larger contribution from that. So in graphical format, I'm going to take a fairly large sigma 2s orbital, and then I'm going to add to that a relatively smaller sigma 2p orbital. As I do that, I think you can see that there's constructive overlap in the middle, and there's destructive overlap on the outside. What that's going to do is it's going to cause the orbital to bulge in the middle and have less electron density on the outside. So when I look at the result, right, some of this energy is going to disappear, and I'm going to have a bigger bulge in the middle. So sigma 1g, it's going to have essentially the same symmetry that sigma 2s had, but its shape is going to be different. Much less electron density out here, and more electron density in the center. Because I'm adding this, I'm going to get a bigger lobe in the middle, it's subtracting some of this electron density away. Which means that when I sweep that around in the third dimension, right, I'm going to end up with an orbital that has a much greater probability of finding the electron density between the nuclei and a smaller probability of finding the electron density outside. That's going to make it a better bonding orbital. It's going to lower in energy relative to the original sigma 2s orbital, because the more electron density between the nuclei, the more strongly bonding it is. And you'll notice if you actually do this, if you make these molecular orbitals in a program that creates molecular orbitals for you, that for diboron, you can actually see the nuclei. Within the 90% probability surface, you can actually see the nuclei in an end-on view. Whereas for difluorine, F2, the sigma 2s orbital actually has a little bit of a dip in the middle. It's not a cucumber so much as a stretched out. So the electron density between the nuclei gradually increases as you move from right to left. F2, not as much as O2, O2 not as much as N2. By the time you get to B2, right, almost all the electron density is between the nuclei. So that orbital has dropped in energy. Sigma 1g is lower energy than sigma 2s. Well, if I combine them constructively like that, I'd have to combine them destructively, because it's the rules that say you have to have the same number of molecular orbitals as you started with atomic orbitals, or in this case, the same new molecular orbitals as I had old molecular orbitals. So in addition to forming sigma 1p, I'm going to form sigma 3g star. It'll still have Dorada symmetry. It'll still have two nodes, because sigma 2p had two nodes. And it's going to be some small coefficient of the sigma 1s orbital minus a rather large coefficient of the sigma 2s orbital rather, and some large coefficient of the sigma 2p. Right? So destructive overlap, which means it's going to be an anti-bond or a less bonding orbital. If I put them on a graph, I'm going to start with a pretty large sigma 2p orbital. And then on top of that, I'm going to put a fairly small sigma 2s, but with the opposite sign. So my sigma 2s orbital it doesn't matter which one I change the sign on, right, as long as I've changed the sign on one of them. So what you're going to see is that the destructive overlap is now in the center, and the constructive overlap is now on the outside. Which is going to cause the sum to get larger on the outside and smaller on the inside, so that when we draw that orbital, we've got less electron density in the middle and more electron density on the outside. That leads to less effective bonding and a rise in energy. So sigma 3G, sigma 3G is going to be higher in energy than sigma 2P. It had to be. If sigma 1G dropped relative to sigma 2S, then sigma 3G has to rise relative to sigma 2P, so the sum of those two energies can be the same as it started. So in effect, what we've done is we've made an orbital that's more bonding than it used to be, and we've made an orbital that's less bonding than it used to be. So if we want to put these orbitals on the same energy diagram, sigma 2s will drop and it becomes sigma 1g. That'll be way down there, actually. Off. Sigma 1g will have lowered in energy relative to sigma 2s, that's gone down. And sigma 2p will have risen in energy. And it turns out that sigma 3g, because sigma 2p rises in energy, and it rises by the same amount as sigma 1g drop, sigma 3g actually rises to the point where it's above the pi orbital energy level. The sum of sigma 1g plus sigma 3g is still the same as the sum of sigma 2s plus the sum of sigma 2p. But this is where the key difference is between the orbitals, where sigma 2p has changed relative to the pi orbitals, which gives a separate shape, which leads to a different prediction of the order of orbital filling. So if I did that, I can also form sigma 2u by taking a fairly large coefficient of sigma 2s star, and sigma 2u will still be anti-bonding, and adding to that a smaller coefficient times sigma 2p star, and I can form sigma 4u, which will also be an anti-bonding orbital, by taking a fairly small coefficient of the sigma 2s star orbital, psi 2s star orbital, minus a fairly large coefficient of psi 2p star. So we're going to look at the sigma 2s star orbital, which on a graph looks like this. We have a fairly large coefficient, positive on one side, negative on the other side, and then we're going to take the 2p star orbital and interact that, but a smaller coefficient on the sigma 2p star orbital. So the sigma 2p star orbital will look like this. It had larger lobes on the outside than on the inside. It did a very good job. Larger lobes on the outside than the inside. you'll see that there's constructive overlap here, outside the armed axis, and there's destructive overlap here in the middle. So the sum of that will have gotten bigger out here and smaller in here. But it'll still have the overall shape of the orbital that takes the larger coefficient. It will just have less electron density between the nuclei and more electron density outside the nuclei. So it'll look more like this. It's less effectively anti-bonding. Because the electrons aren't in the middle, because mostly they're on the outside, since they're anti-bonding electrons, that's where you want them, right? So it becomes less anti-bonding than it used to be, which means its energy lowers. So sigma 2U star is still above the original 2s energy level, but not nearly as much above the original 2s energy level as it used to be. We've now got kind of a urn-shaped, looks a little bit like one of those baskets that the snake charmers would pull a cobra out of, where the lower energy orbital drops a lot more relative to the original 2s energy levels than the higher energy orbital, the anti-bonding orbital, goes up. Put that up here. If sigma 2s or sigma 2g, sigma 2u star, it has integral symmetry. If sigma 2u star is lower in energy than sigma 2s star, then sigma 4u star must be higher in energy than sigma 2p star. It's going to have to go up here somewhere. And when you consider the diagram that shows the two high energy orbitals, it's going to look like an upside down snake charmer's basket. So this basket relative to that basket have similar symmetry, which means that the sum of sigma 1g plus sigma 2u star plus sigma 3g plus sigma 4u star is going to be the same as the sum of sigma 2s, but the two lower energy orbitals drop in energy while the two higher energy orbitals rise in energy. So we've taken the sigma system that used to look like that and moved it like that. What does this one look like? Well, sigma 4u star is going to start with a fairly large coefficient on sigma 2p star. Right? Sigma 2p star will look like this. And then it's going to add to that a sigma 2s star, but a fairly small coefficient. So it's going to take this sigma 2p star, or it's going to take the sigma 2s star orbital, but not much of the sigma 2s star orbital, and it's going to flip the sign so that it looks like this. And that makes the destructive overlap out here. And the constructive overlap here in the middle. Its shape is going to be about the same as the kind of, or it's where the nodes are going to be very similar to where they were for the sigma 2p star orbital, that the shape is going to change so that we have increased electron density between the nuclei and decreased electron density on the outside of the nuclei. So it's going to look more like this. And then when you turn that into your blobs, what you're going to have is much larger orbitals in the middle, our new node. So where sigma 2u star had less electron density between the nuclei and more outside, sigma 4u has more electron density between the nuclei and less on the outside. This makes it more effectively anti-bonding. And if it's more effectively anti-bonding, it should rise in energy, which is what we predicted it had to do, right? Less effectively anti-bonding means it drops in energy. More effectively anti-bonding means it rises in energy. So we've changed the fundamental shape of the orbital energy diagram from looking like a mace to looking like a violin. Kind of looks like a fiddle. So without SP mixing, you've got a mace shape, and with SP mixing, you've got a fiddle shape. The crucial difference being the location of the sigma 3G orbital relative to pi y and pi z. So let's use that knowledge of what the orbital diagram looks like to consider what the envelope picture for diatomic boron would look like, D2. Right? Boron comes with 3 valence electrons. You might predict that it could take energy diagram would look like that, or maybe you'd say that it would be an energy diagram that looked like that, or a Lewis structure rather, or maybe you'd say that it could be a Lewis structure that looked like that. It's kind of hard to draw a good Lewis structure for diatomic boron. It just doesn't really work. But it's not hard to draw a molecular orbital picture for diatomic boron. We have a fairly small delta E, which means we have SP mixing. Electrons. So we know that we have sigma 1d down here and sigma 2u star. And so sigma 2u star is a little bit above the 2s orbital energy level, and sigma 1g is quite a bit below. Sigma 3g will now be a little bit below the original P energy level, and sigma 4u star would be quite a bit above. And we know that pi y and pi z will be below, and pi star y and pi star z will be above. And that those will be symmetrically distributed about the original 2p orbital energy level, so that we have the overall shape of item with sigma 3g above pi y and pi z. We have 6 electrons. We can now put those electrons into the orbitals. First one in sigma 1d, second one spin pairing, much less energy than the gap up to sigma 2u star. And then the third one here, the fourth one, again, there's a larger amount of energy between sigma 2u and between pi y and pi z than there is spin pairing energy. And then the last two will go into pi y, and then the degenerate pi z orbital to maximize the spin by 1 joule. So we would predict that diatomic boron, B2, is paramagnetic, which is in fact observed. And we would predict a bond order of 4 bonding electrons minus 2 anti-bonding electrons divided by 2, or a bond order of 1. So we predict effectively a single bond. So the best Lewis structure that we could draw that would be consistent with the observed properties of diatomic boron based on the molecular orbital diagram would be this one. Now the bond order is actually a little bit more than 1, because this orbital is so much more bonding than this one is anti-bonding. This doesn't really cancel out as effectively as the simple calculation of the bond order would suggest. So this is stronger than you might predict for an ordinary boron-boron bond, because the net energy of the bonding electrons has dropped by a lot more than the net energy of the anti-bonding electrons has risen. So you might think that maybe this is a reasonable Lewis structure as well, because it shows that the bond is going to be a little bit shorter than the bond that we predicted. This is probably the one you would have drawn if you were trying to draw it just using Lewis structures, and you want to try to maximize the number of electrons on each one and get each one as close to a field octet as possible. But there's no support for that in the actual properties, because this would predict that boron would not be paramagnetic, it would be diamagnetic, and it would predict that the boron-boron bond is much shorter and stronger than is actually observed. So this is what the orbital energy diagram looks like for diatomic boron, for diatomic carbon, and for diatomic nitrogen. The difference being only the number of electrons that are in each system. So we now know how to draw the orbital energy diagrams, molecular orbital theory, for first and second order diatomics, either with or without sp mixing.